For decades, black holes have been treated as the ultimate destination in the cosmos, a place where matter vanishes from view and every path leads inward. But some of the deepest equations in physics point toward a possibility that is even more unsettling. What if there are regions of the universe where the flow of reality runs in the opposite direction? Not objects that consume, but objects that release. Not gateways into darkness, but eruptions from a hidden realm beyond observation. Such an object has never been seen, never been confirmed, and may not even be allowed to exist. Yet it continues to appear in the mathematics of gravity and spacetime. If it is real, it could transform our understanding of black holes, cosmic origins, and the structure of the universe itself. Tonight, we investigate the forbidden white hole, the mystery that may begin where every black hole comes to an end. The history of science is filled with ideas that were eventually abandoned. Some theories survived only a few years before evidence proved them wrong. Others remained popular for centuries before new discoveries replaced them with better explanations. In most cases, once an idea fails to match observation, it gradually disappears from serious scientific discussion. White holes are unusual because they never completely vanished. Despite never being observed, never being confirmed, and never becoming part of accepted astrophysical reality, they continue appearing in some of the deepest equations describing gravity and spacetime. They occupy a strange position in modern physics. Most scientists remain skeptical of their existence, yet mathematics refuses to erase them. To understand why, we must begin with black holes. When Einstein developed the theory of general relativity, he revealed that gravity is not simply a force pulling objects together. Gravity emerges because massive objects distort the geometry of spacetime itself. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. Soon after Einstein published his equations, physicists began exploring their consequences. Among the solutions they discovered was something extraordinary. Under certain conditions, matter could collapse so completely that it would create a region from which nothing could escape. Not light, not information, not even time in the familiar sense. This prediction eventually became the modern black hole. Black holes seemed almost impossible, yet observation after observation confirmed their existence. Astronomers found evidence of their gravitational influence. They detected stars orbiting invisible objects with enormous mass. They observed powerful emissions from matter falling into these dark regions. Eventually, humanity even captured the first images of black hole shadows. Black holes moved from theory to reality. Yet hidden inside the same equations was another possibility. If a black hole represents a region where everything moves inward, then mathematics also allows the opposite. A region where everything moves outward, a region that cannot be entered from the outside, a region that only releases. This theoretical object became known as a white hole. The concept immediately raised questions. A black hole behaves like a one-way entrance. Once something crosses the event horizon, returning becomes impossible. A white hole would behave as a one-way exit. Matter and energy could emerge from it, but nothing could enter. The symmetry was elegant. The implications were disturbing. A white hole seemed to violate common expectations about how the universe behaves. Black holes form naturally through the collapse of massive stars. Scientists understand the processes that create them. White holes appeared to have no obvious formation mechanism. Nothing in ordinary astrophysics seemed capable of producing such an object. Many researchers assumed white holes were mathematical curiosities rather than physical realities. Yet the idea refused to disappear. The reason is that white holes are not inventions added to the equations. They emerge naturally from the same framework that successfully predicts black holes. Remove the white hole entirely, and important symmetries within spacetime solutions begin to change. The mathematics continues hinting that such objects remain possible, even if nature rarely or perhaps never creates them. This is what makes white holes so fascinating. They are not merely science fiction concepts. They arise from some of the most successful equations ever developed. The universe seems unwilling to confirm them. Physics seems unwilling to forget them. The mystery became even deeper. researchers began noticing surprising connections between white holes and some of the biggest unresolved problems in cosmology. Questions about information loss inside black holes, the nature of singularities, and the earliest moments of the universe all seem to brush against ideas related to white holes. Each connection renewed interest. Each unanswered question kept the possibility alive. Imagine finding a door repeatedly marked on different maps, even though no explorer has ever seen it. Every attempt to remove the door from the maps creates inconsistencies elsewhere. Every investigation leads back to the same mysterious symbol. Eventually, curiosity becomes unavoidable. White holes occupy a similar place in modern physics. They remain hidden. They remain controversial. Yet they continue appearing at the edges of our understanding. They do not exist. They are mathematical ghosts, created by the structure of Einstein's equations. They represent something real that humanity has not yet learned how to recognize. That uncertainty is precisely why physicists continue returning to the idea. White holes sit at the intersection of mathematics, gravity, and cosmic mystery. They challenge assumptions about beginnings and endings. They force researchers to ask whether black holes truly represent the final destination of matter and information. Because if the equations are pointing towards something more, then the next question becomes unavoidable. What would the universe look like if it contained a one-way exit instead of a one-way entrance? The most remarkable feature of a black hole is that it creates a one-way journey. Matter can enter, but it cannot return. Light can cross the event horizon, yet once it does, every possible path through spacetime leads deeper inward. The geometry of reality itself becomes tilted toward collapse. This is why black holes are often described as cosmic traps. They do not merely pull things inward through gravity. They reshape the structure of spacetime so completely that escape becomes impossible. For many years, physicists assumed this was the end of the story. Then they noticed something curious hidden within Einstein's equations. The same mathematics that allows a one-way entrance also permits a mirror image. If spacetime can be arranged so that every path leads inward, then under certain mathematical conditions, it can also be arranged so that every path leads outward. Instead of trapping matter and energy, such a region would expel them. Instead of functioning as a destination, it would function as an origin. This strange possibility became the foundation of the white hole concept. To understand why this idea is so unusual, imagine a waterfall. Water continuously flows over the edge and downward. Anyone standing nearby can easily see the direction of movement. Now imagine encountering a waterfall, where the water emerges from empty space at the bottom and races upward toward the sky. The phenomenon would appear completely backward compared to ordinary experience. A white hole creates a similar reversal within spacetime. A black hole gathers matter into an increasingly dense region. A white hole would do the opposite. Matter, energy, and radiation would emerge outward from a central region that cannot be entered from the outside. Every possible trajectory would point away from the object rather than toward it. What makes this idea especially fascinating is that the difference is not merely about motion, it is about the direction of causality itself. In a black hole, future events pull everything inward. In a white hole, the structure of spacetime would push everything outward. The object would behave as though reality were flowing away from a hidden source. This raises an immediate question. If white holes are mathematically possible, why has nobody ever seen one? The answer is that a white hole would be extremely difficult to form. Nature provides clear mechanisms for creating black holes through stellar collapse and gravitational compression. White holes appear to require the opposite process, a spontaneous emergence of matter and energy from an inaccessible region. No known astrophysical event clearly produces such behavior, yet the absence of observation does not completely eliminate the idea. Some physicists argue that white holes may be extremely short-lived. Others suggest they could exist under rare conditions that have not yet been identified. A few theories even propose that what appears to be the death of a black hole might eventually lead to the birth of a white hole after immense periods of time. The possibility remains controversial, but it refuses to disappear. What keeps the mystery alive is the fact that a white hole would solve a profound conceptual problem. Black holes seem to represent an ultimate ending, a place where matter disappears from view. A white hole would represent the opposite, a beginning emerging from somewhere hidden beyond observation. Together, they form two halves of a deeper symmetry embedded within spacetime. Whether nature actually allows such objects to exist remains unknown. Yet the mathematics continues pointing toward a remarkable possibility. The universe may not be built entirely around destinations and collapse. Somewhere within the structure of reality, there may also be exits, origins, and pathways moving in the opposite direction. And if such a one-way exit truly exists, then another question naturally follows. What kind of boundary separates a region where everything falls inward from a region where everything is forced outward? The most fascinating idea in modern physics is that black holes are not simply objects floating in space. They are regions where the geometry of spacetime becomes so extreme that the normal rules governing movement and escape are fundamentally altered. The event horizon of a black hole is often described as a boundary, but it is not a physical surface like the shell of a planet or the wall of a building. Nothing solid exists there. Instead, it marks a point where the structure of spacetime changes in a profound way. Outside the event horizon, escape remains possible. A spacecraft can fire its engines and move away. A beam of light can travel outward into the cosmos. The future still contains routes leading away from the black hole. Cross the horizon, however, and the situation changes completely. Inside that boundary, every possible future points inward. No matter what direction an object attempts to move, all available paths lead deeper toward the center. Escape does not become difficult. It becomes impossible because the geometry of reality itself has been rearranged. This is what makes the white hole concept so intriguing. If a black hole contains a boundary where collapse becomes unavoidable, then a white hole would contain a boundary where the opposite occurs. Instead of every future leading inward, every future would lead outward. The structure of spacetime would force matter and energy away from the central region rather than toward it. Imagine standing on a hillside where every slope descends toward the same valley. No matter which direction you choose, gravity eventually guides you downward. This resembles the spacetime geometry surrounding a black hole. Now imagine a landscape where every path rises away from a central point. Movement naturally carries everything outward. This is closer to the strange geometry associated with a white hole. The boundary separating these behaviors is one of the most mysterious features of the theory. In a black hole, the event horizon acts as a one-way threshold into collapse. In a white hole, the horizon would become a one-way threshold into escape. Nothing could cross inward because the geometry would forbid such a journey. Matter, radiation, and energy would only move outward from the hidden interior. What makes this possibility especially interesting is that the boundary is not merely a division between two regions of space. It represents a transition between two completely different directions of spacetime behavior. On one side, reality funnels everything toward a concealed destination. On the other side, reality continuously releases material from a concealed origin. Some theoretical models suggest that these two types of horizons may be more closely connected than they first appear. In certain solutions of Einstein's equations, a black hole and a white hole can emerge as different aspects of the same spacetime structure. The black hole represents the region where paths converge. The white hole represents the region where paths diverge. Whether such a structure can exist in the real universe remains unknown. No observation has yet revealed a confirmed white hole horizon, yet the mathematics continues pointing toward a hidden boundary where collapse gives way to escape, and where the familiar direction of gravitational flow appears to reverse itself. If such a boundary truly exists, it raises an even deeper mystery. What happens to the information that enters a black hole? Could a white hole provide a pathway through which that information eventually returns to the universe rather than disappearing forever? Among all the mysteries surrounding black holes, few have challenged physicists more deeply than the question of information. At first glance, the problem appears simple. Matter falls into a black hole. The black hole grows larger. Everything seems straightforward. Yet hidden within this process is a puzzle that reaches into the foundations of modern physics and has occupied some of the greatest scientific minds for decades. The puzzle begins with a principle that lies at the heart of quantum mechanics. According to our best understanding of the quantum world, information cannot simply disappear from reality. Physical systems change, particles interact, objects transform into other objects. Yet the underlying information describing those systems must remain preserved. This principle is so important that many physicists regard it as one of the most fundamental rules in nature. Black holes appear to challenge that rule. Imagine a library containing millions of books. Every page holds information. Every sentence records a pattern. Now imagine placing the entire library into a black hole. The books vanish beyond the event horizon. Their pages become inaccessible. Their contents can no longer be read. This does not seem like a serious problem. The information still exists somewhere inside the black hole. The deeper difficulty emerged in the 1970s when physicists began studying a phenomenon now known as Hawking radiation. According to the work of Stephen Hawking, black holes are not completely eternal. Through subtle quantum effects near the event horizon, they slowly lose energy. Over incredibly long periods of time, a black hole can gradually shrink and eventually disappear. This discovery transformed the information problem. If a black hole eventually evaporates, what happens to everything that fell inside it? The matter disappears. The black hole disappears. Where does the information go? If the information is truly destroyed, quantum mechanics faces a profound crisis. One of its most fundamental principles would be violated. If the information survives, then some mechanism must exist for preserving it. For decades, physicists have debated possible solutions. Some theories suggest information is encoded within Hawking radiation itself. Others propose that information remains stored on the event horizon. Still others argue that our understanding of black holes remains incomplete. This is where white holes enter the story. One of the most intriguing possibilities is that black holes may not represent the final stage of the process. Instead, they may be part of a larger cycle. Imagine a river disappearing underground through a cavern. From the perspective of someone standing at the entrance, the water seems lost. It vanishes into darkness. The journey appears complete, yet many underground rivers eventually reappear elsewhere. The water was never destroyed. It simply traveled through a hidden region before emerging again. Some physicists wonder whether information entering a black hole could behave in a similar way. Rather than being erased, it might pass through an inaccessible phase of spacetime and later emerge through a white hole. In this scenario, the white hole would function as a release mechanism. The information swallowed by the black hole would not remain trapped forever. Instead, it would eventually re-enter the observable universe. This idea becomes especially fascinating in certain models of quantum gravity. According to some proposals, matter collapsing into a black hole never reaches an infinitely dense singularity. Quantum effects become dominant before such an extreme state can occur. The collapse slows, transforms, and eventually reverses. From the perspective of an outside observer, the black hole may appear stable for enormous spans of time. Deep inside, however, a different process could be unfolding. The collapse could transition into expansion. The black hole could evolve into a white hole. In this picture, information is never destroyed. It is delayed. What appears to be a final destination becomes a temporary phase. The information disappears from view, only to re-emerge later through a white hole-like event. The implications are extraordinary. Every star consumed by a black hole. Every particle crosses an event horizon. Every fragment of matter swallowed during billions of years of cosmic history. None of it would be lost forever. Everything would remain encoded within spacetime, waiting for a future release. Of course, enormous challenges remain. Even if such a process occurs, the timescales involved may be almost unimaginable. Some calculations suggest that a black hole might take far longer than the current age of the universe before transitioning into a white hole. The information could remain hidden for periods so vast that entire cosmic eras pass before its return. This raises another fascinating possibility. What emerges from a white hole might not resemble the original objects that entered the black hole. A library thrown into a black hole would not necessarily emerge as neatly organized books. The information could return in highly transformed forms. The patterns survive. The original arrangement may not. A useful comparison comes from burning a sheet of paper. The paper disappears. Smoke rises, ash remains. The original object is gone. Yet in principle, the information describing the paper still exists within the arrangement of particles produced by the process. Recovering it would be extraordinarily difficult. The information survives even though the original form does not. A white hole could operate in a similar manner on a cosmic scale. Information returns. Its original appearance may not. What makes this possibility so compelling is that it offers a bridge between two of the deepest ideas in modern physics: the gravitational world of black holes, the informational world of quantum mechanics. Instead of forcing one theory to surrender to the other, the white hole concept provides a potential pathway through which both principles remain valid. Black holes continue swallowing matter. Quantum information remains preserved. The contradiction dissolves. Whether nature actually works this way remains uncertain. No observation has confirmed that black holes evolve into white holes. No experiment has detected information emerging from such objects. The idea remains speculative, yet it remains one of the most fascinating possibilities ever proposed. Because if white holes truly release information that black holes appear to consume, then black holes cease being cosmic graveyards. They become cosmic transformations, not endings. Transitions, not destruction. Delay. And if information can eventually return through a white hole, then another question immediately emerges. Could such events have already happened somewhere in the universe without being recognized for what they truly are? Could astronomers have already observed the signatures of white holes while interpreting them as something entirely different? The most fascinating aspects of the white hole mystery is that the question may not be whether white holes exist, but whether they have already appeared without being recognized. This possibility sounds surprising because white holes are often described as purely theoretical objects. No telescope has ever identified a confirmed white hole. No scientific paper has announced the discovery of one. No observation has settled the debate. Yet the universe is filled with events that remain only partially understood. Astronomy often progresses by observing something unexpected and then spending years, sometimes decades, trying to determine what produced it. The history of science contains many examples of phenomena that appeared mysterious before their true nature became clear. Pulsars were once so unusual that some researchers jokingly considered the possibility of alien civilizations. Quasars puzzled astronomers because they released extraordinary amounts of energy from extremely small regions. Even black holes themselves were regarded with skepticism before overwhelming evidence confirmed their existence. Because of this history, some physicists have wondered whether white holes might already be hiding among cosmic events that currently lack complete explanations. The idea begins with a simple observation. If a white hole exists, it would not quietly sit in space like an ordinary star. A white hole is defined by release rather than accumulation. Matter and energy would emerge outward from it. The event would likely be dramatic, energetic, and highly visible across enormous distances. This means astronomers should not expect white holes to appear as dark objects waiting to be photographed. They would more likely resemble sudden eruptions, powerful bursts, or unexpected releases of energy. This possibility has led researchers to compare white holes with some of the most extreme events observed in the universe. One candidate that has occasionally entered these discussions is the gamma-ray burst. Gamma-ray bursts are among the most energetic explosions ever detected. For a brief period, they can outshine entire galaxies. These bursts release enormous amounts of energy in very short intervals, creating flashes visible across billions of light years. Today, many gamma-ray bursts are explained through collapsing massive stars or mergers involving neutron stars. Observations have provided strong evidence supporting these explanations. Yet some physicists have asked whether certain unusual bursts might represent something different. What if a white hole event could appear as a sudden release of energy without a conventional source? Imagine observing a tremendous explosion in a distant region of space and then discovering that no star existed there beforehand. No gradual buildup occurred. No obvious precursor appeared. Matter and radiation simply erupted into existence and expanded outward. Such an event would strongly resemble the theoretical behavior expected from a white hole. This does not mean gamma-ray bursts are white holes. Most evidence points toward more conventional astrophysical explanations. The significance lies elsewhere. The comparison demonstrates that a white hole would likely appear as an explosive release rather than as a stable object. This realization changes the way scientists think about the search. Looking for a permanent cosmic structure, researchers may need to look for brief and unusual events. Another intriguing possibility emerges from theories connecting black holes and white holes. Some quantum gravity models suggest that black holes may eventually transform into white holes after extremely long periods. The collapse does not continue forever. Instead, quantum effects halt the process and reverse it. In this scenario, a white hole is not a separate object appearing independently. It is the future state of a black hole. What makes this idea remarkable is that the transformation could occur very rapidly from the perspective of the black hole itself, while appearing delayed from the perspective of outside observers. The result could resemble a sudden release of matter and energy from an object that had previously appeared stable. If such transitions occur somewhere in the universe, astronomers might witness only the final eruption without realizing they are observing the last stage of a process that began billions of years earlier. This possibility has inspired some researchers to investigate unexplained transient events, searching for signatures that might distinguish white hole behavior from ordinary astrophysical phenomena. The challenge is that nature already produces many spectacular explosions. Supernovae release enormous energy when stars die. Neutron-star collisions generate powerful bursts of radiation. Active galactic nuclei produce jets stretching across vast distances. The universe is not short on dramatic events. A genuine white hole would need to exhibit characteristics that clearly separate it from these known processes. So far, no observation has achieved that standard. Nevertheless, the search continues because white holes remain theoretically interesting. Another reason some physicists take the possibility seriously involves the early universe itself. Certain speculative models propose that what we call the Big Bang may share properties with a white hole. The comparison should be treated carefully, because the Big Bang is not simply a white hole in the conventional sense. Both concepts involve matter and energy emerging from an extremely dense state and expanding outward. From a certain perspective, the Big Bang resembles a cosmic release event rather than a collapse event. This similarity has encouraged some researchers to explore whether white hole physics might offer insights into the origins of the universe. If so, then humanity may already be living inside the aftermath of the largest white hole-like event imaginable. The idea remains highly speculative, yet it illustrates how deeply the white hole concept reaches into cosmology. The most compelling reason the mystery persists is that modern astronomy constantly encounters phenomena that challenge expectations. New telescopes reveal structures never seen before. Unexpected signals appear from distant regions of space. Transient events emerge and disappear before complete explanations can be established. The universe repeatedly demonstrates that it is capable of surprising even the most experienced researchers. White holes occupy a unique place within this landscape of possibilities. They are not arbitrary inventions. They emerge naturally from solutions of Einstein's equations. They offer potential answers to unresolved questions about information, black holes, and spacetime, and they remain difficult to rule out completely. This combination keeps the idea alive despite the lack of direct evidence. Imagine discovering footprints in a forest without seeing the animal that created them. The tracks may be incomplete, alternative explanations may exist, yet the possibility remains that something unseen passed through the area. White holes occupy a similar position in modern physics. The object itself has never been observed. Certain clues continue pointing toward possibilities that remain unresolved. The evidence is not strong enough for confirmation. The mystery is not weak enough for dismissal. And that uncertainty creates one of the most intriguing questions in cosmology. If white holes have already appeared somewhere in the universe, perhaps hidden among explosive events that astronomers have not fully explained, then what kinds of cosmic eruptions should scientists be searching for? Because scattered across the observable universe are bursts of energy so extreme and so unusual that some researchers still wonder whether they represent entirely new categories of astrophysical phenomena waiting to be understood. The universe is often described as orderly because the same physical laws operate everywhere we look. Stars are born through recognizable processes. Galaxies evolve according to patterns astronomers can study. Planets follow predictable orbits shaped by gravity. This consistency is one of the reasons science works so well. It allows researchers to observe an event, identify the mechanism behind it, and build models capable of predicting similar events elsewhere in the cosmos. Yet every so often, the universe presents something unexpected. A signal appears that does not fit comfortably within existing explanations. An eruption releases more energy than anticipated. A burst arrives from a location where no obvious source exists. An event unfolds so quickly, or so intensely, that astronomers are forced to reconsider their assumptions. These moments are important because they reveal the limits of current understanding. Most eventually receive explanations as better observations become available. Some remain partially mysterious for years. A few continue provoking debate long after their discovery. This is where the white hole discussion becomes particularly interesting. White holes have never been observed directly. No scientist can point to a confirmed object and say with certainty that it is a white hole. Yet if white holes exist, they would likely announce themselves through extraordinary releases of matter and energy. They would not appear as subtle phenomena. They would resemble cosmic eruptions powerful enough to attract immediate attention. Because of this, researchers occasionally ask an intriguing question. Could some unexplained eruptions represent processes that modern astrophysics has not yet fully identified? To understand why this question arises, it helps to consider how scientists investigate unusual cosmic events. When a powerful burst of radiation reaches Earth, astronomers do not automatically know its origin. They must reconstruct the event using indirect evidence. They study the duration of the signal. They examine its spectrum, they determine where it came from, and search for related observations across multiple wavelengths. The mystery is solved. A collapsing star becomes a supernova. A pair of neutron stars merges. Matter falls into a supermassive black hole. The event gains an explanation and joins the growing catalogue of understood phenomena. Not every case proceeds so smoothly. The universe occasionally produces signals that resist immediate classification. One famous example involves fast radio bursts. When these signals were first detected, astronomers were astonished. Extremely brief, yet incredibly powerful flashes of radio energy appeared from distant regions of space. They lasted only fractions of a second, yet during that tiny interval they released astonishing amounts of energy. Nobody knew what caused them. Speculation flourished. Some proposed exotic astrophysical mechanisms. Others suggested entirely new categories of cosmic objects. As additional observations accumulated, researchers identified likely explanations involving highly magnetized neutron stars known as magnetars. Yet the early uncertainty illustrates an important point. The universe is capable of producing events that initially seem inexplicable. White holes enter scientific conversations because they belong to the category of ideas that might explain certain classes of unexplained eruptions if ordinary explanations fail. Another example comes from gamma-ray bursts. These events represent some of the most energetic explosions ever observed. For a brief moment, they can release more energy than entire galaxies emit over much longer periods. Modern astronomy has successfully explained many gamma-ray bursts through stellar collapse and compact object mergers. Nevertheless, the sheer scale of these eruptions demonstrates that nature is capable of generating phenomena that would have appeared impossible before they were understood. A hypothetical white hole event could produce similarly dramatic behavior. Matter emerging suddenly from a hidden region of spacetime would release enormous amounts of energy. The eruption could appear without the gradual buildup associated with ordinary astrophysical processes. Observing a star evolving toward collapse, astronomers might witness a sudden release, seemingly emerging from nowhere. Such an event would be deeply puzzling. The challenge, of course, is distinguishing a genuine white hole from other powerful phenomena. The universe contains many mechanisms capable of producing explosions: supernovae, neutron star mergers, magnetar flares, active galactic nuclei, and tidal disruption events all generate extraordinary energy. A white hole explanation would only become compelling if observations revealed features that existing models could not reproduce. This requirement is one reason white holes remain speculative. Science favors explanations grounded in observed mechanisms. Before invoking an entirely new category of object, researchers exhaust conventional possibilities, yet the mystery persists because some questions remain unresolved. For example, certain theoretical models predict that black holes may eventually transition into white holes through quantum gravitational processes. If such transformations occur, the resulting eruptions could differ from known astrophysical events in subtle ways. The challenge is that these predicted signals remain uncertain. Researchers do not yet know precisely what they should look like. Theoretical descriptions vary. Observational signatures remain difficult to identify. Astronomers cannot confidently search for white holes in the same way they search for stars or galaxies. The object remains hidden behind layers of uncertainty. This uncertainty becomes even more intriguing when considering the early universe. The cosmos we observe today emerged from conditions so extreme that many familiar physical intuitions cease to apply. The temperatures were enormous, densities reached extraordinary levels, spacetime itself behaved differently from the universe we know now. Some speculative ideas suggest that processes resembling white holes may have played roles during these early stages, not necessarily as isolated objects, but as manifestations of deeper spacetime dynamics operating under extreme conditions. Such proposals remain highly controversial. They illustrate how the white hole concept extends beyond individual objects and enters broader questions about cosmic evolution. The most fascinating aspect of all this is that science progresses through anomalies. Most discoveries begin as observations that do not fit existing expectations. The orbit of Mercury helped reveal limitations in Newtonian gravity. Unexpected atomic behavior contributed to the birth of quantum mechanics. Strange radio signals led to the discovery of pulsars. Again and again, nature advances knowledge by presenting puzzles. White holes survive in scientific discussions because they occupy the territory of unresolved possibilities. No evidence currently proves they exist. No evidence completely eliminates them. The idea remains suspended between theory and observation, waiting for future discoveries to clarify its status. Imagine standing on a shoreline during a storm and seeing enormous waves emerge from the darkness. Most can be traced to familiar causes. Wind patterns explain their behavior. Ocean currents reveal their origins. Then one wave appears different. Its source is unclear. Its behavior is unusual. Its explanation remains incomplete. The appearance of a single anomaly does not immediately rewrite oceanography. It does, however, create a reason to investigate further. The same principle applies to astronomy. Most cosmic eruptions eventually find explanations within known physics. Yet every unexplained event keeps the door open to deeper possibilities. And among those possibilities is the idea that somewhere in the universe, hidden beneath processes we do not yet fully understand, reality may occasionally produce phenomena resembling the long-theorized behavior of a white hole. If that possibility is true, then the mystery becomes even larger. Because a white hole, would not merely be an unusual object. It could represent a connection to something beyond ordinary spacetime itself, a gateway not simply releasing matter and energy, but perhaps linking our universe to regions of reality that remain completely beyond observation. Among all the ideas associated with white holes, none stretches the imagination further than the possibility that they are not merely unusual cosmic objects, but connections to something beyond the observable universe. This concept moves beyond questions about stars, black holes, and astrophysical explosions and enters a much deeper territory. It asks whether space-time itself may contain pathways linking regions of reality that normally remain completely separated from one another. To understand why this possibility emerged, it helps to remember something important about general relativity. Einstein's theory is not simply a theory of gravity. At its deepest level, it is a theory describing the geometry of space-time. Matter influences that geometry, and the geometry influences how matter moves. Because of this relationship, Einstein's equations do more than describe planets and stars. They reveal surprising possibilities hidden within the structure of reality itself. When physicists explored those equations, they discovered that space-time could possess far stranger architectures than anyone had expected. Under certain mathematical conditions, space-time can bend, twist, and connect in ways that have no equivalent in ordinary experience. One of the most famous examples is the concept of a wormhole. A wormhole is often described as a tunnel connecting distant regions of space-time. Instead of traveling across the enormous distances separating two locations, an object could theoretically pass through the tunnel and emerge elsewhere. Whether such structures can exist in nature remains uncertain, but the mathematics demonstrates that space-time may be capable of far more complex arrangements than a simple three-dimensional landscape. White holes entered these discussions because they sometimes appear in theoretical models connected to wormholes and extended black hole geometries. In certain mathematical solutions, a black hole and a white hole can be linked through a hidden region of space-time. The black hole acts as an entrance. The white hole acts as an exit. Matter entering one side could, in principle, emerge from the other. This picture is highly idealized and likely does not describe real astrophysical black holes exactly as they exist in nature. Nevertheless, it introduced a remarkable possibility. What if a white hole is not creating matter? What if it is releasing matter that originated somewhere else? This question changes everything. Viewing a white hole as an isolated object, it becomes part of a larger system. The material emerging from it may have traveled through regions inaccessible to ordinary observation. The white hole becomes less like an explosion and more like a doorway. Imagine standing beside a mountain and seeing water emerge from a cave. To an observer at the cave entrance, the water appears to come from nowhere. Yet the water may have traveled through underground channels extending far beyond what is visible from the surface. A white hole could function in a similar way. The matter emerging from it may not originate locally. It may arrive from hidden regions connected through deeper structures of space-time. Some physicists have even explored the possibility that black holes inside our universe could connect to entirely different universes. This idea belongs to the realm of speculative theoretical physics, but it arises naturally when researchers investigate the mathematical consequences of certain space-time geometries. In these models, reality becomes much larger than the observable cosmos. The universe we know would represent only one region within a broader structure. Black holes and white holes could act as bridges between domains that normally remain disconnected. If such a picture were correct, a white hole would not simply release matter into space. It would release matter from somewhere beyond the observable limits of our universe. This idea remains controversial for good reason. No evidence currently confirms the existence of other universes. No observation has demonstrated a functioning bridge between separate regions of reality. Yet the possibility remains fascinating because it emerges from attempts to understand gravity at its deepest level. The mystery becomes even more intriguing when considering what happens inside a black hole. According to classical general relativity, matter collapsing into a black hole eventually approaches a singularity. a region where density becomes extreme and the known laws of physics cease to provide meaningful descriptions. Many physicists suspect that singularities are not physical objects but signs that our theories have reached their limits. If quantum effects replace the singularity with a more fundamental process, entirely new possibilities emerge. Instead of terminating in a point of infinite collapse, space-time may continue into a different phase. The black hole becomes a transition rather than an ending. The white hole becomes a reappearance rather than a beginning. The connection between them transforms what seemed like separate objects into parts of a larger structure. This concept has inspired some of the most ambitious ideas in modern cosmology. Certain models propose that our own universe may have emerged from a process resembling a white hole event. In these scenarios, the Big Bang itself is interpreted not as the absolute beginning of existence, but as an emergence from a prior space-time configuration. The details remain speculative, and no consensus exists regarding such models. Their significance lies in what they suggest about the nature of reality. They imply that beginnings and endings may not be as absolute as they appear. A black hole may not represent the end of a journey. A white hole may not represent the start of one. Both could be transitions between different regions of a much larger cosmic structure. Another reason this idea continues attracting attention is that it addresses a philosophical puzzle hidden within modern physics. The observable universe contains horizons beyond which we cannot see. Black holes contain horizons beyond which information cannot directly return. Reality already includes regions separated by fundamental limits. If such boundaries exist, it becomes natural to ask whether other inaccessible domains may also exist. White holes provide one theoretical mechanism through which those domains might occasionally reveal themselves. Imagine living in a vast house while only being able to access a single room. The walls surrounding the room prevent direct observation of the rest of the structure. Yet occasionally a door opens and something enters from beyond. You may not know what lies outside. You know only that the larger structure exists. A white hole could serve a similar role within space-time. It could represent a place where something hidden becomes visible. Something beyond observation enters the observable universe. Something from another region of reality briefly announces its presence. The most important point is that these ideas remain possibilities rather than established facts. Modern physics has not confirmed that white holes are gateways. It has not confirmed that other universes exist. It has not demonstrated that black holes connect to distant regions of space-time. The value of these concepts lies in the questions they encourage scientists to ask. Questions about the true structure of space-time. Questions about what lies beyond observable horizons. Questions about whether reality extends far beyond the portion we can currently study. And if white holes truly function as gateways from another region of reality, then an even deeper mystery emerges. Because such objects would not merely connect different places, they might connect different eras, different phases of cosmic history, perhaps even different directions of time itself, which leads directly to one of the most profound questions in the entire white hole mystery. Could these strange objects be connected not only to distant regions of space, but to the very origin of time itself? Few questions in science are as profound as the question of time. Human beings experience time so naturally that it often feels invisible. We remember the past, we live in the present, we move toward the future. Every event in our lives appears to follow this sequence. The growth of a tree, the movement of a planet, the aging of a star, and the expansion of the universe all seem to confirm that time possesses a direction. Yet when physicists examine the deepest laws of nature, they encounter something unexpected. Many of the fundamental equations describing reality do not strongly prefer one direction of time over another. Mathematics often works just as well whether time moves forward or backward. This discovery creates a mystery. If the laws themselves are largely indifferent to direction, Why does the universe appear to have such a clear arrow of time? Why do broken objects not spontaneously reassemble? Why do memories point toward the past rather than the future? Why does the cosmos appear to evolve from earlier states toward later ones? These questions lead directly into one of the strangest aspects of the white hole concept. A white hole can be understood as a kind of time-reversed black hole. To appreciate what this means, imagine watching a video of a black hole swallowing matter. Gas spirals inward. Radiation falls toward the event horizon. Everything moves toward collapse. Now imagine reversing the video. Matter erupts outward. Energy escapes from a hidden interior. The collapse becomes expansion. The black hole begins to resemble a white hole. This comparison is not merely a visual trick. The mathematical relationship between black holes and white holes is deeply connected to the symmetry of Einstein's equations. In a certain sense, the white hole represents what a black hole would look like if the direction of time were reversed. This observation immediately links white holes to one of the greatest mysteries in physics, the origin of temporal direction itself. Why does the universe seem to prefer one direction of time rather than the other? The connection becomes even more intriguing when we consider the early universe. Modern cosmology suggests that the universe began in an extraordinarily ordered state. Shortly after the Big Bang, matter and energy existed under conditions very different from those observed today. As the cosmos expanded, complexity increased, stars formed, galaxies emerged, structure developed. The arrow of time appears deeply connected to this process. Many physicists believe that the direction of time is tied to the increase of entropy, a measure often associated with disorder and the number of possible arrangements available to a system. The universe began in a remarkably special state. Since then, entropy has generally increased. This progression creates the temporal direction we experience. White holes enter the discussion because they seem to violate ordinary expectations about entropy. A black hole consumes matter and energy from the outside world. Everything moves inward toward greater compression. A white hole appears to do the opposite. It releases matter from a hidden source. To some researchers, this behavior resembles the emergence of a low entropy state from conditions that should not naturally produce one. The resemblance is striking enough that certain physicists have wondered whether white holes might provide clues about why the universe began in such an unusual condition. The comparison becomes even more fascinating when considering the Big Bang itself. The Big Bang is often misunderstood as an explosion occurring inside pre-existing space. In reality, it represents the rapid expansion of space-time itself from an extremely dense and hot state. Everything moves outward. Everything emerges. Everything expands. At a superficial level, this behavior resembles the theoretical description of a white hole. For this reason, some speculative models have explored whether the observable universe could be connected to a white hole-like process. These ideas remain controversial and far from established science. The Big Bang is not simply a white hole according to mainstream cosmology. Nevertheless, the comparison continues attracting attention because both phenomena involve matter and energy emerging rather than collapsing. Both involve outward evolution. Both raise questions about the origins of space-time. This connection becomes even deeper when researchers investigate what may happen inside black holes. Classical relativity predicts that matter collapsing into a black hole eventually reaches a singularity, a region where known physics breaks down. Many physicists suspect that singularities are not physical realities, but signs that current theories are incomplete. Quantum gravity may replace the singularity with something entirely different. In some theoretical models, the collapse eventually reverses. The black hole transitions into a white hole. The inward journey becomes an outward journey. The ending becomes a beginning. If such processes occur, then black holes and white holes are not separate objects. They become different phases of the same space-time structure. This idea introduces a remarkable possibility. The distinction between beginnings and endings may be less absolute than it appears. A collapse may contain the seed of an expansion. A disappearance may precede a re-emergence. An ending in one region of reality may become a beginning in another. This perspective naturally leads to questions about the origin of time itself. Suppose the universe emerged from a process related to a white hole-like transition. Suppose the Big Bang represented not the absolute beginning of existence, but the emergence of a new space-time region from a deeper structure. Time as we know it may have begun not from nothing, but from a transformation occurring beyond our observational horizon. The arrow of time would become part of a larger story. The beginning of our cosmic history would no longer represent the beginning of all reality. It would represent the beginning of the particular temporal direction experienced within our universe. Some modern theories explore related ideas through concepts such as bouncing cosmologies, cyclic universes, and quantum gravitational transitions. These models differ in important details, yet they share a common theme. The apparent beginning of the universe may not be the ultimate beginning. A deeper process may exist beneath it. White holes frequently appear in these discussions because they provide a mathematical example of how spacetime can transition from collapse to expansion. Another fascinating aspect of the white hole-time connection involves observation itself. From the perspective of an external observer, a white hole appears profoundly unnatural. Matter emerges from a hidden region without an obvious cause visible from the outside. Yet this perception may reflect the limitations of the observer rather than the true nature of the process. A person watching only one chapter of a story may mistake a continuation for a beginning. Similarly, a white hole event could appear mysterious because the earlier stages remain hidden beyond accessible spacetime. What looks like spontaneous creation may actually be the continuation of a deeper process occurring elsewhere. This possibility transforms the meaning of time, viewing reality as a simple line running from beginning to end. The universe may contain structures where different temporal phases connect through hidden geometries. Black holes, white holes, and cosmic origins become parts of a larger network of relationships linking collapse, emergence, and transformation. The most profound implication is that white holes force physicists to reconsider one of their most basic assumptions: the assumption that the direction of time is fundamental. It may not be. The flow of time could emerge from deeper conditions. The beginning of the universe could represent the appearance of a particular arrow of time rather than the beginning of existence itself. White holes remain speculative. Their existence has not been confirmed, yet they continue appearing at the intersection of some of the deepest questions in cosmology. Questions about origins, questions about entropy, questions about space-time, questions about why time flows in the direction we experience. And if white holes truly possess a connection to the origin of time, then another mystery naturally follows, because understanding their role would require answering an even more difficult question. What would an observer actually see if they approached one of these forbidden objects and witnessed its strange relationship with space-time firsthand? What would reality look like near a place where the ordinary rules of beginnings and endings appear to reverse themselves? The most fascinating questions surrounding white holes have nothing to do with equations, theories, or mathematical models. It concerns experience. If a white hole truly existed somewhere in the universe, what would it actually look like? What would an observer witness while approaching one of the strangest objects ever proposed by physics? The challenge in answering this question is that white holes remain hypothetical. No telescope has identified a confirmed example. No spacecraft has approached one. Everything scientists discuss about their appearance comes from theoretical predictions based on general relativity and related models. Even so, those predictions paint a remarkable picture. To understand it, we must first forget many of the visual assumptions created by science fiction. White holes are often portrayed as glowing portals floating in space, surrounded by dramatic colors and obvious distortions. real physics suggests something much stranger. Imagine observing a black hole from a safe distance. A black hole does not appear as a cosmic vacuum cleaner pulling everything around it into a visible funnel. Instead, it appears as a region where gravity becomes so extreme that light itself behaves in unusual ways. Matter spiraling inward forms a bright accretion disk. Radiation is emitted from the surrounding environment. The event horizon itself remains dark because light cannot escape from it. A white hole would reverse some of these behaviors. Instead of matter falling inward, matter would emerge outward. Instead of radiation disappearing toward a hidden center, radiation would stream away from it. The object would appear less like a destination and more like a source. An observer watching from far away might see powerful emissions spreading into space. Particles, energy, and radiation could emerge from a region that seems disconnected from any conventional origin. What makes this especially strange is that the observer would never see anything entering the white hole. This is one of the defining features of the concept. A black hole accepts incoming matter. A white hole rejects it. Every trajectory that attempts to move inward is prevented by the geometry of spacetime itself. Imagine standing beside a river where every current flows away from a central spring. No matter how hard you try to move upstream, the flow continuously pushes outward. A white hole would create a similar situation within spacetime. The closer an observer attempted to approach, the more unusual reality would become. According to theoretical descriptions, the event horizon of a white hole functions as a one-way boundary. Matter can emerge from it. Matter cannot cross into it. If a spacecraft attempted to enter such a region, it would encounter an increasingly hostile environment. Outward-moving radiation and particles would flood the surrounding space. The energy released could be enormous depending on the size and nature of the white hole. This means that approaching a white hole might be far more dangerous than observing one from a distance. The environment near the object could be filled with intense radiation, energetic particles, and violent space-time effects. Yet the most fascinating aspects of the experience may involve light itself. General relativity predicts that gravity influences the path of light. Around massive objects, light bends. Images become distorted. The appearance of distant stars changes. Near a black hole, these effects produce dramatic visual phenomena. Background objects appear warped around the event horizon. Light follows curved paths through spacetime. The geometry of vision itself becomes altered. A white hole would likely produce similar distortions. Because matter and radiation are moving outward rather than inward, the visual experience could differ in important ways. An observer might witness streams of energy expanding from a central region while surrounding light is bent by intense gravitational fields. The result could be a strange combination of brightness and distortion unlike anything found elsewhere in the universe. Another intriguing possibility involves time. One reason white holes attract so much attention is their relationship to time-reversed solutions of Einstein's equations. While this does not mean that clocks literally run backward near a white hole, it does mean that the object is connected to unusual temporal structures within spacetime. For an observer watching from afar, the behavior of matter near the white hole could appear deeply unnatural. Imagine witnessing material emerge from a hidden region without observing the processes that created it. The event would seem to violate ordinary expectations about cause and effect. Everyday experience teaches us that outputs follow inputs. A white hole appears to provide outputs without visible inputs. The observer sees emergence without witnessing origin. This is one reason the object feels so mysterious. It challenges intuitive ideas about how events unfold. Some theoretical models suggest that if white holes are connected to black holes through deeper spacetime structures, the material emerging from a white hole may have originated elsewhere entirely. An observer would be witnessing matter arriving from a region that cannot be directly observed. The white hole becomes less like an object and more like an interface between different domains of spacetime. This possibility introduces another fascinating question. What would the emerging matter actually look like? Would it resemble ordinary gas and radiation? Would it carry signatures of extreme gravitational environments? Would it appear in highly organized forms or chaotic bursts? Current theories do not provide definitive answers. The details depend on the specific model being considered. Some scenarios predict explosive eruptions, others suggest more gradual releases. Still others envision brief events lasting only short periods before disappearing. This uncertainty reflects a larger truth about white holes. They remain theoretical possibilities rather than established astrophysical objects. Scientists can describe how space-time behaves around them. They cannot yet describe every detail of their appearance with confidence. Perhaps the most unsettling aspect of observing a white hole would be psychological rather than physical. Human intuition is built around certain assumptions. Causes precede effects. Objects originate from visible processes. Matter comes from somewhere we can identify. A white hole challenges all of these expectations. An observer would witness material, energy, and radiation emerging from a region that appears disconnected from any observable source. The event would seem to blur the distinction between origin and destination. What appears to be a beginning may actually be the continuation of something hidden. What appears to be creation may actually be released. The deeper one thinks about it, the stranger the picture becomes. A white hole would not simply be an unusual astronomical object. It would represent a direct challenge to some of the most basic assumptions people hold about space, time, causality, and cosmic structure. Standing near such an object would mean confronting a region where the universe behaves according to rules rarely encountered elsewhere. A place where emergence replaces collapse. A place where escape replaces capture. A place where matter arrives without revealing where it came from. And if humanity were ever fortunate enough to observe a genuine white hole, the implications would extend far beyond the object itself, because confirming its existence would not merely solve a mystery, it would force physicists to rethink black holes, information, space-time, and perhaps even the fundamental architecture of reality, which leads directly to the final question in the white hole story. What discovery would finally convince scientists that white holes are real? And how would that discovery transform our understanding of black holes forever? For more than a century, black holes have transformed from mathematical curiosities into some of the most important objects in modern science. What began as an unexpected consequence of Einstein's theory of general relativity eventually became an observational reality. Astronomers discovered stars orbiting invisible gravitational giants. Powerful telescopes detected matter spiraling into dark regions of space-time. Gravitational wave observatories recorded the collisions of black holes billions of light-years away. Humanity even captured images of the shadows cast by these extraordinary objects. Each discovery strengthened the same conclusion: black holes are real. Yet, despite all this progress, one profound mystery remains unresolved. What truly happens inside them? The answer matters, because black holes sit at the intersection of the two greatest theories in modern physics. General relativity describes their gravitational behavior with remarkable accuracy. Quantum mechanics governs the microscopic rules that appear to control information and fundamental particles. Individually, both theories are extraordinarily successful. Together, they create a puzzle that has resisted solutions for decades. At the center of that puzzle lies the question of information. If matter falls into a black hole, and the black hole eventually evaporates through Hawking radiation, what becomes of the information describing everything that entered it? Some theories suggest information remains encoded in subtle ways. Others propose entirely new mechanisms for preserving it. No consensus has yet emerged. This is why the discovery of a genuine white hole would be so revolutionary. It would not simply add another exotic object to the cosmic inventory. It would force scientists to reconsider the entire life cycle of black holes. For decades, black holes have been treated primarily as endings. Matter falls inward. Information becomes inaccessible. The object grows larger. Every path points toward deeper collapse. White holes suggest a radically different possibility. Black holes are not endings at all. They are transitions. Imagine reading a novel while missing its final chapter. Every event appears to move toward a conclusion, but the story remains incomplete. Certain mysteries remain unresolved because a crucial part of the narrative is missing. The discovery of a white hole could provide the missing chapter in the story of black holes. Suddenly, processes that seemed final might reveal themselves as stages within a larger sequence. Collapse could lead to emergence. Disappearance could lead to reappearance. The implications would extend far beyond astrophysics. One of the first consequences would involve the information paradox itself. Suppose astronomers discovered evidence that matter emerging from a white hole carried signatures connected to material previously absorbed by a black hole. Such evidence would suggest that information is not destroyed, it is transformed. It disappears from one region of spacetime and reappears in another. The paradox would not vanish instantly, but the entire discussion would shift. Researchers would move from asking whether information survives to investigating how information travels through hidden phases of spacetime. Another extraordinary consequence would involve singularities. Classical general relativity predicts that matter collapsing into a black hole eventually reaches a singularity, a point where density becomes extreme and known physics ceases to provide meaningful predictions. Many physicists suspect that singularities do not actually exist in nature. Instead, they may signal the breakdown of current theories. If white holes were discovered and shown to be connected to black holes, the singularity might no longer represent the final destination of collapse. The singularity could be replaced by a transition process governed by quantum gravity. This would represent one of the most important breakthroughs in theoretical physics. For decades, researchers have searched for a framework capable of uniting quantum mechanics and gravity. White holes could provide observational clues pointing toward that deeper theory. The consequences would not stop there. A confirmed white hole would force scientists to rethink the architecture of spacetime itself. At present, spacetime is often imagined as a continuous structure containing stars, galaxies, black holes, and other familiar objects. White holes suggest something more complex. They hint at hidden pathways, unseen regions, and geometric connections extending beyond ordinary observation. If such structures exist, then the universe may possess a richer topology than currently understood. The observable cosmos could represent only part of a much larger spacetime network. This possibility naturally raises questions about cosmic origins. For generations, physicists have attempted to understand what happened at the beginning of the universe. The Big Bang marks the earliest stage that modern cosmology can reliably describe. Yet deeper questions remain. What preceded it? Why did it occur? How did spacetime itself emerge? Some speculative models propose connections between white holes and cosmic beginnings. The discovery of a white hole would not automatically confirm those ideas, but it would make them far more difficult to ignore. Researchers would suddenly possess evidence that spacetime can produce outward emerging structures resembling certain theoretical descriptions of cosmic origins. Entire branches of cosmology would receive renewed attention. The most dramatic consequence would be philosophical. Science progresses by identifying patterns in nature and building explanations around them. Black holes currently represent some of the strongest examples of irreversible processes in the universe. Matter falls inward. Escape becomes impossible. The story appears complete. White holes challenge that narrative. They suggest that some endings may conceal hidden continuations. Some disappearances may conceal hidden transformations. Some destinations may be gateways rather than conclusions. The discovery would therefore alter not only scientific models, but also the way people think about causality, emergence, and the structure of reality. Imagine discovering that a door, long believed to be a wall, was actually an entrance to another room. Everything previously understood about the building would need to be reconsidered. The rooms remain real. The structure remains real. The overall picture becomes much larger. White holes could have a similar effect on cosmology. Black holes would remain real. General relativity would remain powerful, yet the larger picture of spacetime would expand dramatically. Of course, extraordinary claims require extraordinary evidence. Science does not accept ideas because they are fascinating. It accepts them because observations demand them. A genuine white hole discovery would require clear, repeatable evidence that cannot be explained through existing astrophysical processes. Researchers would need observations demonstrating behavior fundamentally different from known objects. The standards would be extremely high. Yet history shows that the universe often surprises us. Black holes themselves were once regarded as implausible. Gravitational waves were once considered almost impossible to detect. Many of today's accepted discoveries began as controversial possibilities. This is what keeps the white hole mystery alive. Not certainty, possibility. The possibility that somewhere in the universe exists an object capable of revealing that black holes are not the final chapter of gravitational collapse. The possibility that information is not lost but transformed. The possibility that space-time contains structures more complex than current theories fully describe. The possibility that one discovery could connect quantum mechanics, gravity, black holes and cosmic origins into a single deeper story. And perhaps that is the most important lesson of all. The forbidden white hole remains unconfirmed. It may never be found. It may ultimately prove to be a mathematical possibility that nature never realizes. Yet the questions it raises continue pointing toward the deepest mysteries in physics. Mysteries about information, mysteries about time, mysteries about space-time, mysteries about beginnings and endings. Because if a white hole is ever discovered, the greatest revelation may not be the existence of the object itself. The greatest revelation may be that the universe has been hiding a larger story behind black holes all along. A story in which collapse is not the end, but the beginning of something far stranger than anyone imagined. White holes remain among the most controversial ideas ever proposed in physics. They have never been observed, never been confirmed, and may exist only within the deepest layers of mathematical theory. Yet their significance lies in the questions they force us to confront. If black holes represent the ultimate destination of matter and information, could white holes represent a beginning rather than an ending? Could they reveal hidden pathways within space-time that we have not yet learned to recognize? The mystery of the forbidden white hole is not simply about a strange cosmic object. It is about the possibility that reality is far more complex than the boundaries we currently understand. Somewhere beyond the limits of observation, the answer may already exist. And if a white hole is ever discovered, it could transform not only our understanding of black holes, but our understanding of the universe itself.